now that we have our B tree bushiness invariance, that we know B trees are bushy, let's talk about runtime. So this is a bit of a heavy duty slide, so let me walk you through it. What I'm showing here is a tree which is almost the worst case and a tree which is the best case. And here it's for L equals 2. So this tree on the right, we see that every non-leaf node has only one item, whereas in the best case tree, every non-leaf node has 2 items. The reason this is better is that with more items, you can have more branching. And with more branching, you can have more stuff in your tree for the same height. So for example, in this near worst case tree, we have 8 items and the height is 2. In this best case tree, we're able to cram 26 items into our tree and our height is still 2. So in these two cases, these are the best and the worst case asymptotically. In the worst case, the height grows with log base 2 of n. So as we add more items to a tree with this feature, where the non-leaf nodes all have exactly one item, the height will be log 2. Because at each level, we're doubling the size of the number of items we have available. By contrast over here, the height grows with log 3, because we were able to triple the size of the tree at every level. So the argument then is that between the best and the worst case, the height of a B tree with limit L is going to be between log L plus 1 of n and log base 2 of n. And so since both of these are logarithms of n, we can just drop the base and say that the overall height is theta log n. Okay? So what we've shown now is because B trees are always bushy, they always have this really nice shape, we're always going to be somewhere between this worst case and this best case, and both are theta log n. So what does that mean for our actual operation runtimes? Well, let's think about the contains operation. So if I think about what happens, I want to find some item. I need to do, at worst, I need to look at h plus 1 items. So I look at the root, the next level, the leaf, in this case, where h is 2. Now, in each node, I will have to look at perhaps as many as L things, because the nodes are of width L. So the overall runtime then would be L times h plus 1, and in asymptotic notation, I can say that it's big O of HL. And the reason I'm saying big O here is I'm saying it's the runtime for all possible operations, not just the worst case. Because of course, if I do contains and I find the thing in the root, I'm good to go. So the overall runtime is big O of HL. And so now, in order to simplify this, I will say that since the height is itself log n, the overall runtime is big O of L times log n. Now since L is a constant, because my trees, I specify in advance that this is a 2-3 tree or whatever, then we have that the overall runtime for contains is log n. Great, so we've shown that B trees, because of the bushiness invariance, have a log n runtime for all operations. Add is almost the exact same thing. I'm actually not going to talk through it. And so here, because add and contains are both log n time, our tree, we could think of it as having log n runtimes. Now, one thing we haven't talked about is the deletion operation. And I'm actually not going to do it, but I am including extra slides if you'd like. In them, it walks through the process of how to delete, as well as a little bit of the runtime, but it's not something we expect you to know. It's a little too intricate, and I don't think it's deep enough that I want to make it a primary topic of the course. Okay, so to summarize today, BSTs, as you guys know, they have a best case height of theta log n and a worst case height of theta n. This is a problem. That having a theta n height means theta n runtimes for our operations. Now we noticed, or I mentioned earlier on, that big O is not the same thing as the worst case, and this is something that will be confusing for you, but eventually you'll pick it apart. And I'll have a study guide problem for this lecture that will help you tease apart the difference between big O and worst case theta. Then we talked about B trees. So those were a modification of BSTs that avoided this worst case. In this tree, nodes can have between 1 and L items. Contains is exactly like a normal BST, except that you have to look inside each node, so there's multiple items per node. Add works by adding items to existing leaf nodes, and if they're too full, they split. The resulting tree has perfect balance because of our bushiness invariance, and therefore the runtime for the operations is big O of log n. Now again, I haven't talked about deletion. See the extra slides if you're curious. And we also have not discussed how you would split if L was, say, 1,000. Like, what do you do? Who do you move up? That'll be in some other class. So B trees are more complex. That is true. Like, the code for them is more complex. The way we think about them is more complex. But the nice thing is they can handle efficiently any insertion order, and as it happens, also deletion orders. So that's it for today. If you'd like, make sure to check out the extra slides, which discuss a little bit more about deletes, and I'll see you in the next video, when we'll do a totally different way of balancing trees.